Yeah, good. So let's continue where we were. Hopefully we don't have any technical problems today. I hope that I iron them out. So we were trying to prove this theorem last time. Density of the rational numbers among the real numbers. Specifically, it says that in between any two real numbers, we can always find a rational number. And we get a little bit of an insight of how we were going to do that. And we were right here with this first step of our plan. So we assume that A is less than B, so B minus A is positive. And by the Archimedean property, we know that there is some number that makes 1 over n small as we want. And in this case, this B minus A, we can make it as small as I want. And I mean, B minus A is some fixed number, and we can find an n so that 1 over n is as small as needed. All right. So let's then we use this 1 over n. We're going to find out the rational number that we want. So now this is going to be the denominator. So what we need to specify now is the numerator. So here's the numerator that is going to work. So we're going to let m be this, the floor, the greatest integer part of n times a plus 1. Okay, so now let me remind you what this function is. So in general, this number, the greatest integer of x, is the smallest, I mean, is the largest integer less than or equal x. Right? So for example, if you do the greatest of 5.4, well, that's 5. If you do the floor of 5, well, that's 5 itself because it's already an integer, right? So it's like taking the integer part. It's also called the integer part. So that's what we're doing here. We're taking the integer part of n times a and then adding 1. And we claim that this is the number that works. So we claim that m over n is between a and b. And now let's explain why. Okay, the first part is kind of easy because by definition the integer part, so note that, so the integer part is for sure by definition smaller than or equal n times a, right? That's it's in the definition, is the integer that the greatest one you can pick that is smaller than or equal than na, just by the definition. But because it's the greatest with that property, we also know that it's bigger than na minus 1, because if it was smaller than na minus 1, you could go 1 unit further, right? It means that you didn't pick the largest possible number with that property. So this happens in general. So this is in general. So in general, it's always true that x minus 1 is less than the floor of x, which is less than or equal x. So this property is a general property. It doesn't have anything to do with an. It happens whatever number you get. All right. From here, we can already get this top part because look at what we have here. If we add 1,
Professor,
yeah.
are those brackets?
This is that's exactly what I'm explaining. This is the definition of, so it's not a bracket because it doesn't have it only has the bottom part, right? It only has the bottom part of the bracket, and that's why we call it the floor function or the integer part function. So it's the integer part of a number, like the floor of 5.4 is 5. This is the definition, is the largest integer less than or equal x.
Gotcha. Thank you.
All right. So the inequality we want to establish is the first, this one, that m is bigger than than an, and that's easy, right? Because it's this one over here. See, look at this inequality. If I add 1, what it says is that NA is smaller than the floor of NA plus 1. But this is M, right? You can see it here, right? This is M. So M is bigger than AN. And then if you divide by N, this means that A is less than M over N. So we're done with half of it, right? The left part. And for the second part we can do it a little bit by contradiction. Suppose that this is not true. So suppose, move it up, suppose that m over n is not less than or equal to b, that it is greater than or equal b, okay? What would we do in that case? Well, if that is the case, you can multiply by n both sides, and this is the same as m greater than, I mean, I think I want, yeah, that's okay, bn. And then this is where we use the property of n. The n that we picked was this one. We picked an n such that this fraction is tiny. 1 over n is less than b minus a. So we're going to use that information in here. So because 1 over n is less than b minus a, this means that b is bigger than 1 over n plus a. It's a different way of writing it, correct? And that's what I'm going to write in here. So this is bigger than 1 over n plus a times n. And if we simplify this, you get 1 plus an. And this is a contradiction because to the other inequality, right? Because look over here. We said that m is bigger than na, right? So right now, over here, which is the inequality that I want, yeah, so now is the left inequality here, right? The left inequality over here, what does it tells us? It tells that NA is less than or equal NA. I mean, the floor of NA is less than or equal NA. And if we add 1, as this one over here, but this is M, right? So we're saying that M is smaller than or equal NA plus 1. And compared to the one we just got here, right? This one over here. Well, it's exactly the opposite, right? This one says M is greater than 1 plus A over M. So this is a contradiction. This is a contradiction. And because it's a contradiction, that means the opposite of this happens. So M over N is less than B. And there you have it, right? We just found out our rational number, M over N, which is between A and B. We got it. All right. So then there's a second one that the same way we found a rational number, there's also a way to find an irrational number in between any two reals. And that's one of your homework problems. I'm not going to tell you how to do that, but the book sort of gives you the hints necessary to do that part. Okay, so so moving on, this is the last part that I want to do in from 1.4, and now we actually have a way to properly define square roots, and we're just going to do it with one particular instance as an example. And so this is theorem 1.4.5, and this is what it says. It says there exists a real number alpha, such that alpha squared equals 2. Okay. Now you may be thinking, Professor, do you need to prove this? Well, yes, right. I mean, we are in a sense creating the real numbers, right? Not quite, because we did not construct them precisely, but we're saying what the real numbers are in the following sense. They are an extension of the rational numbers, a field extension, well, that preserves the order and that satisfies the axiom of completeness, right? And now using those properties, now we can prove things like this. We can prove that indeed there is a number such that when you square it, you get 2, right? Remember, this was false for the rational numbers. There is no rational number with this property, right? That's the first thing we proved in this class, going back to the very first meeting. We proved that no rational number, when you square it, you get the number 2. But now with this extension, suddenly you can find solutions to these types of problems. And how do we prove it? Well, here we go. What we need to argue is what is that number, right? We need to show that that number exists. And the extra tool we have is that the supremums and infimums exist. So we're going to define this number alpha as the supremum of some set. That's the key, all right? And here is the set. So consider the set T, and this will be the real numbers such that x squared is less than 2. Okay, so this is a subset of real numbers. And then what are we going to do with this? Well, we're going to check if it's non-empty, and we're going to check if it's bounded. And if it has those two properties, then we can talk about its supremum. And its supremum is going to be the number we're looking for. Okay, that's a way of figuring it out. All right, so here we go. So why is this guy non-empty?
It's in there, 0 is there.
Yeah, 0 belongs in there, for example, right? So note that the number 1 also belongs there. 0 belongs to T. Also 1 belongs to T. So T is definitely not empty. Okay, perfect. So that's the first part. And the second part is it upper bounded? Can we find an upper bound? Can we?
Yeah.
Well, what could be an upper bound of this set?
2.
2, for example. So also, if x is less than 2, then no, that's not what I want. If x belongs to T, right, I want to show that every element in T is less than 2. Okay, how do I do that? Well, if x belongs to T, then x squared is less than 2. That's the definition, right? And the good thing here is we know 2 is less than 4. So this means that the absolute value of x is less than 2. So that means x is itself is less than 2, right? So if the absolute value is less than 2, then the number itself is less than 2, because So 2 is an upper bound, definitely, right? So this set is all less than 2. Okay, great. Yeah.
Professor, on homeworks, would we actually have to prove that it's the upper bound, or like through some type of?
We just did, right?
Okay.
Yeah, this is a proof that 2 is an upper bound, right? Right, because x squared is less than 4, so then you can take square roots on both. I mean, this means that the absolute value of x is less than 2.
I mean, it might be more difficult on certain problems. You might give us.
Yes, absolutely. So,
Professor, is 0 going to be our lower bound?
Is 0 for this set?
Yes.
No, negative. Well, it would be like negative square root of 2, right? Yes. So negative -2 is a lower bound for this set. We don't need a lower bound, but since you're asking, right? It would be similar to this because x is less than 2 in absolute. I mean, what is the meaning of a number being less than 2 in absolute value. It means that its distance from 0 is 2, right? It means that if you go 2 units this way or 2 units that way, that's where the entire set lives. So the entirety of t lives inside this. T is somewhere in here, right? Between -2 and 2. So -2 is definitely a lower bound. Now, there may be better lower bounds or upper bounds, right? In fact, that's the point that where we're going with this. So we're going to talk about now about the supremum. So because this set is non-empty and is upper bounded, we can talk about its supremum. So let's give it a name. And I'm going to call it alpha because I'm already telling, I'm under the strong suspicion that this is the number we need. So we define alpha to be the supremum of t, which it exists because t is non-empty and upper bounded by the axiom. So it exists by the axiom of completeness. Okay, and then what we need to, the rest of the proof is to convince you that this alpha is the number we want. So that this number, when I square it, I get 2. I need to convince you of that. So, and I'm going to tell you the strategy. So to show that alpha squared equals 2, we are going to show that alpha squared less than 2 is impossible, and alpha squared greater than 2 is also impossible. Does that make sense? So if I show you that it cannot be less than 2 and it cannot be greater than 2, well, then the only other possibility is that it is equal to 2, right? So it's a very indirect way of showing that it equals 2. In reality, what we're going to show is that it cannot be less than 2 and that it cannot be greater than 2. And to prove one of the properties, we're going to use that the supremum is an upper bound, and to prove the other property, we're going to use that it is the least upper bound. And this is, by the way, something that happens in general when you use the supremum for some proofs. Usually, you're going to use one property to prove half of it, and then the other property to prove the remaining half. So let's start with alpha squared less than 2. Let's show that that one cannot happen. So let us start with assuming that alpha squared is less than 2. All right, if alpha squared is less than 2, what we're going to do is to show that this guy is not the least upper bound, alpha. So I'm going to find a better upper bound. We're going to find another upper bound that is going to be, let's see, let me just check here if this is the one we're going to, So the one we're going to consider is alpha plus 1 over n for some little n, right? So consider, so we're going to take alpha and we're going to add a little bit to it, right? A tiny, tiny part. We're going to add a 1 over n. And so here's what we want to do. We want to show that there is some n such that alpha plus 1 over n, when I square it, this number is still less than 2, okay? And that would be a problem. I'll tell you why this would be a problem. If we do this, we're done, and I'm gonna tell you why. Because if we do that, this would tell us that this number alpha plus 1 over n belongs to t, right? Let's go to the definition of t. It's right here. T are the numbers such that when you square them, you get less than 2. So this would tell me that this number is in t. Let me write it here. This would imply alpha plus 1 over n belongs to t. But if it belongs to t, that means the supremum has to be bigger than this guy, right? But then the supremum of t, which is alpha, it should be bigger than or equal this guy, right? But that's wrong, because when you take a number and you add a little bit to it, it cannot be smaller than the number itself. So this would be a contradiction. So I just outlined the path we should follow, right? So essentially all we need to do now, all we need to do is to see if we can find an n that makes this happen. Can we find an n that makes this happen? That's all we need to do. Because if we do, then this number would belong to t, and then because it belongs to t, then the supremum is bigger than that number, and this is obviously wrong. That's the idea. Good. So this is all we need to do. Find an n. This is all we need to do. Find an n that makes this happen. Okay. Now, how do we do that? Well, let's try to see what this would entail, right? So this is, I'm going to now show you how you discover the rest of the proof. So I'm not going to want to present to you the clean proof. I want to show you how you could find it on your own, right? So what would you need to do here? Well, you write down what you want, right? This is what we want. We want alpha plus 1 square less than 2. And that's the same as alpha square plus 2 alpha over n plus 1 over n squared less than 2 if you square both sides. And because in general, so here, this is a little trick to simplify this expression. So in general, 1 over n squared is smaller than 1 over n, right? Because you're dividing by something bigger if n is a natural number. So it is enough to show alpha squared plus 2 alpha over n plus 1 over n less than 2. Okay? So if you have this one implies that one because of this inequality. That's why I wrote it is enough, right? So this is not an if and only if. So the arrow here is like this. The bottom one implies the top one because of this. And that's good. And this is convenient because now I can sort of solve for n, right? So from here, this inequality is the same as 2 alpha plus 1 over n less than 2 minus alpha squared, which is the same as 2 alpha plus 1 over 2 minus alpha squared less than n. Okay? And that's it. This tells me what is the n that I need to choose. Choose an n that is bigger than this number. And we can always find a number n as big as we want by the Archimedean property, right? The Archimedean property tells us that you can find a number as big as you want. Okay?
I have a question.
Yes.
So we said the first part where we arrive at a contradiction and then we're saying we want it all over again. Is that just like another way of doing it, or we need to do both?
No. This first part over here, I showed you why this would be enough, right? If I find an n that makes this happen, we're done.
Oh, okay. Right.
But I didn't tell you how to find this n. So that's what I'm doing now, right?
Okay, thank you.
And now this was the discovery, right? This is sort of like, let me put this a little purple rectangle here.
Move the paper down a little.
How we would discover it. And now I'm going to show you how you would write it correctly, right? How would you write it correctly? How do you show that this n exists? You would start from here, right? And this is why sometimes proofs look mysterious, because you never know how the author or the person that created the proof came up with these things, right? But this is why, because they never show you this part, right? When on the very clean proofs, they hide the dirty work. And I showed it to you right now. I show you what happens backstage, so to speak. So here's what you see on the stage, actually. So the neat proof would be like this. So by the Archimedean property, there is some n, a natural number, such that n is bigger than 2 alpha plus 1 over 2 minus alpha squared. Right? I can do that. And then now what I do is I divide by n and multiply by 2 minus alpha squared. And then what I get is that 2 minus alpha squared is greater than 2 alpha plus 1 over n. Right? You see, I'm sort of like writing these things backwards. Then from here, this implies that alpha squared plus 2 alpha over n plus 1 over n is less than 2. If I add alpha squared to both sides of this inequality. Now, since 1 over n squared is less than 1 over n, it follows that alpha squared plus 2 alpha over n plus 1 over n squared is less than alpha squared plus 2 alpha over n plus 1 over n, which is less than 2. This is the one I had before, and this is my new inequality that I'm using here. Oh, you couldn't see. Okay, and this guy over here is actually alpha plus 1 over n quantity squared. And that's it. I'm done, right? I just show you that there is some n such that when I square it, it gives me less than 2. And then that's the end. That's the end of the proof, of half the proof, right? We just showed that alpha squared less than 2 is impossible. That's the one we did. So the other one is done similarly. So lastly, assume that alpha squared is bigger than 2. And this time, instead of looking for alpha plus 1 over n, we're going to look for alpha minus 1 over n. This time, we will consider alpha minus 1 over n. And we want to show there is n, a natural number, such that alpha minus 1 over n squared is bigger than 2. And if this happens, we're going to be done. Why? I'll explain that part, and then we'll see how we can find this n. Okay, but first I'm going to show you why this would be the end of the why we will get a contradiction. Well, because if this happens, then this number would be an upper bound of t. Indeed, if alpha minus 1 over n squared is greater than 2, then for any x in t, what would happen? Remember, what are the x's in t? The x's in t are the ones that when you square them, you get less than 2. Right? X squared is less than 2. But 2 is less than this number. So then that would mean that x is less than alpha minus 1 over n. The, in fact, absolute value of x, but not that it matters, right? Because you have the following. You have that x is less than or equal absolute value of x, which is less than alpha minus 1 over n. So alpha minus 1 over n would be an upper bound of t. Hence, alpha minus 1 over n would be an upper bound of t. But that's impossible. Why is it impossible? Because the least upper bound is alpha. This is impossible because alpha is the supremum, remember? Alpha is the least upper bound. And being the least upper bound means this is the smallest of all the upper bounds. So that means alpha would be smaller than alpha minus 1 over n, right? It would be smaller than any other upper bound. And that's not right, because obviously this number is not bigger than that one, right? Which is a contradiction. So all is left is for us to again find the n that makes this inequality work, okay? And I think it's one of your homework problems to finish this part up, but we can do it here. I don't mind to show you how it would work. So it's very similar. So we can do the dirty work the same as before. So let's put a dividing line here and show what we would need. So what is it that we want? This time around, we want alpha minus 1 over n squared to be bigger than 2. That's the same as alpha squared minus 2 alpha over n plus 1 over n squared bigger than 2. This time around, it's actually easier because we can just remove the 1 over n squared. So this time it would be enough if alpha squared minus 2 alpha over n is bigger than 2, because this other guy is bigger than this one. So again, the bottom one implies the top one, because the top one is even bigger. And from here, you can again solve for n rather easily. This would say alpha squared minus 2 bigger than 2 alpha over n, or n bigger than 2 alpha over alpha squared minus 2. And that's it, okay? That's how you discover what is the n that works. To now write it cleanly, you would start from here, right? You would say by Archimedean principle, there is some n, a natural number, such that n is bigger than 2 alpha over alpha squared minus 2. Of course, right? There is a natural number as big as any number that you want. Then this one would imply that alpha squared minus 2 is bigger than 2 alpha over n. And then that one in turn would imply that the one we want, which is bigger than alpha squared minus 2 alpha over n, is bigger than 2. And this means that alpha minus 1 over n, quantity squared, is greater than 2. And that's it, right? We just found out the n that makes this inequality work. And then you can do the rest of the argument to show that it contradicts the supremum property. Okay? All right. Questions?
Professor, if you look up to saying that 1 over n is greater than 1 over n squared, is the reasoning we're able to ignore that n is equal to 1 doesn't satisfy that inequality, is the fact that we can choose another n?
Where you're saying here?
No, the previous part of the proof. When you prove that it has to be less than 2.
Okay, let me go back. So here.
Yeah, right here.
You're saying which one doesn't work?
Why does it not complicate things? The fact that if n equals 1, it doesn't satisfy the in general statement.
It doesn't satisfy the in. What is the in general statement?
Inside the purple box, in general, 1 over n squared is less than 1 over n. It's not satisfied by n equals 1.
Oh, I see what you mean. I meant like this.
Oh, okay.
Right? Because you have strict, as long as you have one strict inequality, the others are fine. But yes, thank you. This is important. This was important. Yeah.
Right. So I was wondering if that equality ends up messing up any of the logic of the next steps. I guess it doesn't, right?
Let's check. That's a good thing, right? Whenever you change something, let's better go back and check. Where so that would be here, right? It would be less than or equal instead of strict inequality.
Right.
And then that would make this one less than or equal. but it's not a problem because you have a strict
Okay.
one here, right?
Okay, so that one saves it. Okay, thank you.
Exactly. But thank you for noticing. Yeah, that's important. That was a little oversight, right? Had this been my solution, I would have taken a point off from what I written, right? If it was out of 10, right? It's a minor thing, really minor, but it's important to be precise. Good. Thank you. Okay. Moving on. So this is the end of 1.4. So we'll start now the next section, 1.5. And this one is actually a rather nice one. It's about another way in which the real numbers are different from the rational numbers. And it's about cardinality, right? Let me check exactly what the name of, yes, that's what it's called. So 1.5, cardinality. Now I find this concept actually fascinating, and if you ever have the chance of taking a class in set theory, you could actually learn about this concept in general. The idea of cardinality is to see how big a set is. Now that's not a problem if you have a finite set, right? The cardinality of a finite set is just how many elements are in that set. Where it gets really, really interesting is when you have infinite sets. And what we're going to learn in this section, which may be surprising for some of you, is that there are some infinite sets that are bigger than others, right? So when you say infinite, that's really not enough, right? If you ever played this game when you were children of who can say the biggest number, right? And at some point, one of you would say infinite, and you would think you would win. Well, now you are going to find out that there's a way to beat when someone says infinite, because there are infinite sets that are bigger than others, right? And it's surprising, right? In fact, the first person that found out about this, Cantor, really messed up. I mean, that idea really messed up his head in a certain sense. So he had some mental problems because he thought that this couldn't happen, right? He logically arrived to that conclusion, but it seemed like an impossible kind of thing. How is it possible for one infinite to be bigger than other? And okay, but I digress a little bit. So to really talk about this, I mean, we're not going to follow a very long and difficult approach to define cardinals in general, because this class, after all, is not about general set theory. We're concentrating on the real numbers. So for our purposes, the way we're going to go around this is, instead of trying to define what the cardinality of something is, we're simply going to talk about when the cardinality of two sets is the same, okay? And there's an easy way to do this without knowing how big the set is. You can tell when two sets are the same. And the best example to put this in context, something that you could understand, is the following. So imagine a stadium, big stadium, right? And you don't know how many seats there are at the stadium, and there's a lot of people attending that particular event. And you also don't know how many people are there. But here's the thing. You can't tell that everyone is sitting down. So every person at the stadium is sitting in one of their assigned seats, and there are no empty seats, okay? What I did right here is I created a one-to-one correspondence between the people and the stadium seats, right? And even though I don't know how many we have, I hope you are convinced that we have the same number of people as the number of seats, right? Because every seat is occupied and there are no free seats. So the number of the seating capacity of the stadium equals the number of people that came, okay? And that's the idea we're gonna follow. So the important concept here is this notion of having a one-to-one and onto correspondence. So this is a definition that you should be familiar with already. So I'm just gonna write it down to be thorough. If you have a function from A to B, we say that it is one-to-one, or injective. That's another word. If A1 different from A2 implies f of A1 different from f of A2. And this is for every A1 and A2 in A. That's one. That's the definition of an injective function or a one-to-one function. And the companion of this is that we have that a function from A to B is onto or surjective if given a certain B in capital B, there is A in little a in capital A, such that f of little a is B. Right? Intuitively, let me do a picture here. This is what we're talking about. The first one, so here's A and here's B. The first one says that if you have different elements here, they go to different places, right? So if you have A1 and A2, the outcomes must be different. In other words, it's forbidden for two to go to the same, right? The equivalent in our example of the stadium is that it's not okay that two people sit in the same place, right? No sharing of seats. So this is the diagram for one-to-one. And the diagram that would illustrate onto is the following. The diagram for onto is that for all the elements here in B, every one of these guys must have an arrow coming to it. Every single one of them, right? That's the way of saying there are no empty seats. Every one of the seats receives a person. And
to clarify, when you say f from A to B is injective, you would say that f of A1 and f of A2 are in B?
Yes. Yes. Yeah, when you write f like this, it's implied that the outcomes are in the set B. I don't need to write it. It's information you get when you read this over here.
Okay.
So if it is both one-to-one and onto, then we call it a bijection. Right? So that's the other term. If f is both one-to-one and onto, then we say it is a bijection. And then, as I was telling you, to establish when two sets have the same cardinality, think of cardinality as how many elements they have. But again, we're talking the possibility of having infinite sets. All right. So here, here's our definition. Definition 1.5.2. I think the previous one was 1.5.1. We say that the sets A and B have the same cardinality if there is a bijection f from A to B. And we're gonna write in this class, this is not it's not standard notation, but in this class we're gonna write A tilde B, or A is similar to B, to indicate that the two sets have the same cardinality. All right? Let's see some examples. Well, like I told you, if the sets are finite, then it's kind of easy. So for example, this set V of vowels, A, E, I, O, U, I'm not putting Y here, and this set N of the numbers 1 through 5, well, these two sets are equivalent. They have the same cardinality, right? V is equivalent to N. Both of them have the same cardinality. How do you prove this? Well, you tell me a bijection, right? You show me a bijection, and in this case, it's easy. I can, well, just there's many of them, right? There's, as a matter of fact, there's exactly 120 different ways, but here's probably the one you would choose. A goes to 1, E goes to 2, I goes to 3, O goes to 4, U goes to 5, and this is obviously a bijection, right? No two arrows went to the same one, and everyone in here received an arrow. That's it. That's a proof, right? Proof by picture. Okay, so more interesting examples. This is where it gets really, really nice. So let's now put some examples where we have infinite sets. So let me introduce to you this set, blackboard bold letter E. These are going to be the even numbers, the even positive numbers. So 2, 4, 6, 8, etc. Formally, the numbers that you can write as 2n, where n ranges over the natural numbers. And here the claim is that this set E has the same cardinality as the natural numbers, right? Do you see that? What would be the bijection, or one of them?
A bijection from the even numbers to the natural numbers could be for every element in the even numbers divide by 2.
Exactly, very good. So let's define from E to N. You're saying f of E, let's make it E over 2. And it works, and this is well defined because these numbers are all even, so they are all multiples of 2. So when I divide by 2, I indeed get a number, right? And then you would need to argue that it is 1-to-1 and onto, okay? You want to see? So let's check. How do we check it is 1-to-1? To check 1-to-1, usually what one does is suppose 2 arrows go to the same and get a contradiction. So to check 1-to-1, suppose f of A equals f of B for some A and B in the even set, and try to get a contradiction. Well, how do we get a contradiction? Well, from here we get, well, not a contradiction, or, well, you'll see. So f of A is actually A over 2, and this is B over 2. If you multiply by 2, what you get is that A equals B. So that means these guys were not different, right? I mean, I thought I was thinking of 2 numbers that go to the same place, but it's not 2 numbers. They're the same. So there is no contradiction, right? It means that it never happens that 2 different ones go to the same place. And that this is the end, right? This is the end of 1-to-1. So f is 1-to-1. And then to check onto, the way to do it is you show me. You will show me an element in the natural numbers, and you tell me which one goes there, right? To check onto, pick an arbitrary natural number. Natural number, little n. And then who goes there? F of what is n? What would be the one that works?
2n.
Yeah. F of 2n is n, right? And that's it. That's the end of, so f is onto, right? And this is clearly an even number, right? It's 2 times something, so it's perfectly well defined. Beautiful. All right, so more examples. How about n and z, the integers? Turns out that they're also the same size. Okay, and this is weird, right? I mean, well, it already happened here. Even though these two have the same size, the same cardinality, obviously the even numbers are inside the natural numbers, right? So that's already a property that we're not used to if we have infinite sets. So here we can have an infinite set that is inside another one. Let me make a Venn diagram. So here are the even numbers. The even numbers are inside the natural numbers, right? And but they have the same size, right? That's crazy. One is a subset of the other, and they have the same size. The same thing happens here, right? Because the natural numbers are inside the bigger one, which are the integers, and they have the same size again, the same cardinality, and for that matter, the same cardinality as the even numbers. The positive even numbers also have the same cardinality as the integers. All right, good. So how do we come up with a bijection here? There's several ways. So we want a function from the natural numbers to the integers so that it is one-to-one and onto. What do you think? So let me make a little picture. Maybe that can help. Always helps. Pictures are always nice. So here's a picture of the natural numbers. We start at 1, my bad. 1, 2, 3, 4, 5, 6, 7, 8, etc. And here's a picture of the integers. 0, 1, 2, 3, 4, and then -1, -2, -3, etc. Right? So what do you think? How can we make it work? How about, see, this is something we can do. We can take the odd ones and take the odd ones to the positive ones and 0, right? For example, 1, we take it to 0. 3, we take it to 1. 5, we take it to 2. 7 to 3, and so on, right? You see what I'm doing here? I'm taking the odd numbers to go to the positives and 0. And then the even numbers, we take them to the negative ones. Could that work? Would you be convinced that this can work?
Yes.
Now, I can write it down. It's not too difficult to follow on our idea. This is what we're doing with an odd number. So take 1 away from it, and then divide by 2 if n is odd. So that makes this correct, right? If n is an odd positive number, you take 1, and now it's even, and you divide by 2. You can divide by 2, and you get a positive natural number when you do this. And then for the even ones was easy because look, 2 goes to -1, 4 goes to -2, 6 goes to -3, 8 goes to -4. It's easy, right? It's like it goes to half the number and then change the sign. So that's just -n/2. All right, and that's it. So it will take me a little bit of time to check that it is indeed one-to-one and onto. So there is something of a proof to be done here to thoroughly convince you that this is good, but it can be done. All right. Okay. We don't have a lot of time, so one additional example, 1 minute. I don't take time for you.
We have the test.
Exactly. So I'll just take one additional. I'll promptly stop at 1:30. Don't worry about it. So the entire set of real numbers, for example, is the same cardinality as the interval from -1 to 1. Okay, and there's many ways of doing this, but probably the easiest. So here's one way. If I look at the function tangent of pi halves x, right? And if I were to draw you that function, it looks like this. It's like the tangent function, but I multiply by pi over 2. So instead of going, I mean, I think I meant, yeah. So instead of being having asymptotes at negative pi over 2 and at pi over 2, it's going to have asymptotes at -1 and 1 right here. And it looks like this. And you can tell it's 1-to-1 because it satisfies the horizontal line property. And you can tell that it uses all the real numbers. If you look at it sideways, you have all the negative numbers and all the positive numbers exactly once. So the interval -1 to 1 is equivalent to the entire set of real numbers. Okay, I'm going to stop right now.